Well, greetings, Mr. Kolazar's class. What we're going to be looking at is using that information we've done so far with the quantum mechanics model and go with it to actually explain our electron configurations. And so as we're going, the number and the arrangement of electrons around the nucleus of an atom determines its chemical properties. And so we've discussed or started looking into that. But what we're also going to look at is the electrons in these orbitals enter into orbitals in predictable patterns. And so we're going to see where and how they enter in based on three rules. And so these three rules we're going to talk about now. The first one, the Aufbau principle, is that states that each electron occupies the lowest energy orbital available. Now on your chart, these arrows aren't quite all the way fully drawn in. We start up here, and you'll be getting a chart similar to this in class as a review to work through also. And you go from the 1s orbital is where we're going to start at, and then it's going to backtrack, so draw this little backtracking line in to the 2s. That's where first electrons will fit in to the 1s, and we'll back around to the 2s. Once you're done with the 2s filling that one up, it's going to move back around. We're going to move to the 2p, back to the 3s, rotate back up and around to the 3p, to the 4s, rotate back up around, and we're going to go to the 3d, the 4p, the 5s, and back up around and continue this process. Now, as a reminder, the s orbitals can fill 2 electrons max. P can have 6 electrons total or maximum. The D can have up to 10 electrons. And then finally, the F orbital can fill up to 14 electrons each. And we'll break that down again here in a little bit from last section. Our second one, our exclusion principle, states that a maximum of 2 electrons can occupy a single orbital if they spin in opposite directions. So remember, we'll have one electron spin one way and one spin in the other, where we say we kind of have a spin up and a spin down can go together. As long as they're spinning in opposite directions, they can occupy the same orbital. That's where we're able to get 2 electrons in the same orbital. Remember from last one, circle orbital. Our spherical one is our s orbital. 2 electrons maximum can fit in there. And our third rule, Huns rule, states that equal energy orbitals are filled singly before doubly. And so the idea here is that kind of like if you can have your own room, you have your own room, and then if you can't have your own room, then you have to share a room. But the maximum, remember, 2 electrons is the maximum that can fit in any orbital. So to begin with, our s orbital, spherical orbital, can hold a maximum of 2 electrons. So as we're going, we would have our first electron and second electron enter there. On your page, just enter in that says this is your first electron and your second electron. Now, hydrogen has 1, helium has 2 electrons, but most atoms have more than 2 electrons. At that point, they need to start entering in to the next orbital or to our p orbital. They need to enter in singly. So if you have one more electron, the third electron would enter singly, and singly would be our next set of electrons. Now if we have more electrons, then, E minus, not the minus 5. If we have more electrons, then they pair up singly before doubly. So our 6th, 7th, and 8th electrons and 8th electron all enter in singly first, and once they've singled, then doubly, I don't know if that's even a word, or that they pair up secondly. So then again, we end up with a total of 6 electrons in our p orbital. Remember, our p orbital can hold up to a total of 6 electrons. 6 electrons is maximum for the p orbital. At that point, if we have more electrons, they would need to fill the next energy level. So they would just continue on from there, using our last rule, our Aufbau principle, with how they'd fill from energy level to energy level. Now our next rule, our idea, is the orbital notation. Orbital notation diagrams are models of electron arrangement that shows how electrons are distributed in the sublevels and orientations. So each orbital or orientation is represented by a box. The box up there. And in each box, we're going to show the electrons and how they spin. Remember, we can have an up or down arrow to represent the spin. You can either use a full double-headed arrow, or I prefer just using a single-headed arrow, and then down, double-headed arrow, or down would be a single arrow. So our orbital orientation, which we were showing on the last page, I'll just move back one. We've shown the models here. Instead, we're going to have each one of these represented just by a box. So our s orbital would have one box. Our p orbital would have 3 boxes. Each box, remember, can hold up to 2 electrons, because each box is going to be one of those orbital orientations. So we're going to try, if you skip to the back or the second to back page in your notes, you have listed out some orbital orientations. So we're going to work through a few of these problems together. Now, another version of looking at this, we have our 1s, and then 2s, and then as our Aufbau principle says, the next lowest energy level, the 2p, then the 3s, and then the 3p, 4s, 3d, and 4p are the energy levels of increasing energy, so lowest to higher energy level. And in each one of these boxes is our orbital orientation. 2 electrons can fit into each one of these boxes. So as we're going to look at a few of these ideas here. First off, hydrogen element 1 outer electron. So in that 1 outer electron, we just place that in the first energy level. And it's going to be just 1 up arrow in the 1s section. Our second one, helium, has a total of 2 electrons. 2 electrons, both will fit into that first energy level or first orbital. So we put 1 electron facing up and 1 electron down. So 2 total electrons in the helium energy level, or first energy level, are in that 1s orbital. And that's all the electrons that can fit there. If there were more electrons, we would need to put them in the second energy level. And more electrons after that would fit into the next energy level. So carbon, 6 atomic number, so 6 protons, so S has 6 electrons. So we're going to put the first 2 electrons in S, our 1s's level, or excuse me, orbit. If we have more electrons, we still have more. The next ones go into the 2s. Now remember, the s's can only fill up to 2 electrons. And the p can fill up to 6 electrons. So if we still have more electrons, they go into the next energy level. So our next one and 2, spinning up, spinning down, go into the 2s orbital. There are more electrons still available. We've used 4, 2 are left, so we're going to put them into the p orbital. Now note that our other rules said that a maximum can 2, and then Huns rule said singly and then doubly. So we're going to put 1 in the p orbital, and then in the next box we're going to put the second one. Now if there were more, we would continue and put a single one into our next orbital, and then we would start pairing them together. Pairing them together and pairing them together. And then if there were more, they would move on to the next one. I would like you to try out fluorine and potassium. Pause and unpause after you've done those 2, and then we'll finally go through scandium together. Alright, so welcome back. Fluorine. Remember, fluorine has 9 total protons, atomic number, so 9 electrons. 9 electrons, we'd put 2 in the first energy level, or S1. 2 would go in the 2s, and then we'd go single, 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 and then we would pair and then pair up. And at that point, we have our 9 total electrons. 2 in the S1, 2 in the S2, 1, 2, 3, 4, 5, plus our original 4 gives us our 9 total electrons for fluorine. Potassium, 19 total electrons. We start out 2 in the first S, 2 in S2, 3, pair, pair, pair. Work through and always remember, start out going single, 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 pair, 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 so we get in that habit. Single, single, pair, or single, 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 pair, pair, pair. Now notice we have 18 electrons showing, so the 19th electron is going to be placed in that 4s orbital. And then scandium, element 21, as we're going, has 21 total electrons, so we start out single, 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 pair, 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 pair in the S, single, 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 pair, 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 single, pair, and we have one more electron. The next lowest energy level available is the D. We put 1 electron into that D orbital. So our orbital notation, each box can have up to 2 electrons in it, spin up and spin down. Going back into your notes, we're going to look at electron configuration. Shorthand way to represent exactly how the electrons are distributed. So if we were to look, this would be an example. This one would be of helium, is what we're looking at up here. What I would like you to include for helium is, please write in, first off, our energy level is going to be this number 1. So what energy level are the electrons filling in? The S tells us the shape. Is it going to be S, P, D, or F? And then the number written as a superscript up in the air, superscript, is going to be the number of electrons. So it's going to be our shorthand way to write it. This is a common one looking down below. 1s2, 2s2, 2p3, where we have our first energy level. The s orbital has 2 electrons in it. The second s orbital has 2 electrons in it. And in our second energy level, the p orbital has 3 electrons in it. So we have a total of 1, 2, 3, 4, 5, 6, 7 electrons being represented. The element that we'd be looking at in this case would be nitrogen. So that would just be an example of what we're going to start building or creating now by how many electrons are being actually shown. Very similar to what we just looked through with the arrows going spinning up and spinning down. So we're going to jump to that back page in your notes, or the second to back page, for a few practice problems. So we're going to write the electron configuration for those elements that you just looked at. First element, hydrogen, 1s, or 1 electron, and it's going to be in that first energy level. So our first energy level in the s orbital, 1 outer electron, is going to be our electron configuration, or shorthand way to write that. Helium, 1s2, 2 total electrons, both of them in the first energy level in the s orbital. Carbon, 6 total electrons is its atomic number, so 6 total electrons. We're going to show our 1 in the first, 2 in the first orbital, 2s2, 2 in the second, 2p2, 2 in the p orbital. At this point, I'm just going to jump back a slide just to show what we looked at already. All we're doing is, instead of writing out all of the boxes and information for each one, are 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, as we're going through to put those electrons in. Hydrogen, we have 1 electron in the 1s orbital. Helium, 2 electrons in the 1s orbital. Carbon, 2 electrons in the 1s, 2 electrons in the 2s, and then 2 electrons in the 2p orbital. And then we're going to look fluorine, potassium, and scandium next, so you can just jump back in your notes, but I won't jump back after this point. So helium was the 1s1. Our hydrogen was helium, the 1s2. Carbon, we've got 6 total electrons to show. 1s2, 2s2, 2p6, so we have a total of 2, 4, 6 total electrons. Fluorine then, 1s2, 2s2, 2p5. We have our 2 plus 2 plus 5 gives us our total of 9 electrons. Potassium, 19 total electrons. So if you were to look back to that last page, showing how many electrons you have in each orbital, remember we can have a total of 6 electrons in the p orbital. So as we're going, 1s2, 2 electrons in the first, 2 electrons in the second s orbital, 6 electrons in the 2p orbital, 2 electrons in the 3s orbital, 6 electrons in the 3p, and finally 1 lone outer electron in the 4s orbital. And then scandium, going through 21 total electrons. We actually go all the way from the s, from 4s, and we open up the 3d. Now going all the way back to the Aufbau principle from earlier in your notes, after we get from 4s filled, 2 electrons can go in the s orbital. The next lowest energy level is the 3d, and we would have 1 total electron in there. A couple weird exceptions to the rule that you're going to need to know are chromium and copper. Chromium has 24 total electrons, so if we were to start putting them in, 2 electrons in the S1, 2 in the 2S, 6, 1 single, 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 pair, 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 in the 2P, pair in the 3S, single, 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 pair, 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 3, and now we've got up to 24. It looks something like this is what we should have. Now what chromium does that's unusual is you see how we've got single, 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 and an open one, and we have a single one here, our pair here. Chromium actually takes one of its electrons and has everybody singled out to give everybody a little bit more room. So chromium does that. It's very stable. You hear about chrome, a lot of metal on cars. It's very stable doing this. So chromium's exception, instead of being 4s2, 3d4, it moves and is now a 4s1, 3d5. Everybody in this group on the periodic table with chromium, we'll hear about groups going up and down coming up, does a similar process. Copper also is our other exception. Copper, 29 total electrons. So it starts out pairing up S1, 1s and 2s, single, 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 pair, pair, pair for P. Our 4s is filled, and then we get to the 3d, and we end up filling all but that last slot in the 3d. Now copper should look like this, but what copper does as the exception to the rule is it also takes an electron from the 4s to fill the 3d, and it would rather have that d energy level filled, so it literally takes one of those electrons and moves it on over. So copper is the other exception, where copper takes one of the 4s's and moves it to a full d orbital. 2 other elements, silver and gold, do this also. They're in the same group as copper, and they all have very similar properties to them. The reason they do that is to achieve a lower energy state or lower energy ability. We'll start practicing in these in class.